In this lecture, we're going to start discussing something called conformational isomers. And to get into that, though, we need to first look at some properties of molecules called free rotation. So what I want to start with is this idea called free rotation. So, sorry, let me get the sound a little better. I want to start with this idea of free rotation over carbon-carbon bonds. Okay, so it turns out that sigma bonds are able to do free rotation or are able to freely rotate. It's kind of awkward the way I'm going to write this, but I feel like it's a good starting place for us. So sigma bonds, written this way, are able to do free rotation. That is to say, they can freely rotate. That looks a little gross, sorry. Get my handwriting better here. Now, in free rotation, what we're talking about is this idea of a bond that's able to spin the atoms that it's attached to. So in free rotation, one of the bonded atoms, and I'm talking about two atoms bonded together, as is what we've seen so far. We have two atoms bonded together. One of the bonded atoms can spin or rotate relative to the other. Okay, so what we've looked at so far are two very important ideas. Sigma bonds are able to freely rotate, and then we've defined what free rotation is. It's this ability to kind of spin relative to another bond. And if we just look at a quick example of it using our molecules, I've got two carbon atoms. I use these as my tetrahedral models. What I'm going to do is attach the two carbon atoms, one with green hydrogens and the other one with white hydrogens. And what we're saying with free rotation is we have a left side and a right side carbon atom, and carbon is the black ball. And between the left and right side, I can spin one of them relative to the other one. Okay, so this one's, the back one in this perspective is staying put, but the front one is spinning, and this is what free rotation is. We can kind of spin or rotate one of the atoms relative to the other. And by Newton's laws, both, I guess, are kind of spinning. It's just one is fixed relative to the other one is spinning. You could have the left or the right one spin. Okay, so my point so far is that's what free rotation is, and sigma bonds can do it. That's converse or counter to what pi bonds can do. Pi bonds cannot undergo free rotation or do not freely rotate. Okay, and that is to say, to be as specific as possible, is anytime there is a pi bond, free rotation is not possible between the bonded elements. So free rotation is not possible between the bonded elements. So pi bonds, it does not work, and sigma bonds, it does work. Maybe there's a way to look at this from a molecular orbital view. So let's do a molecular orbital view, excuse me, of free rotation. And we're going to first look at sigma bonds. So let's pick on the molecule ethane. We now know that ethane is this 2-carbon fundamental hydrocarbon. It looks like this. That is to say, it has a formula of C2H6. So I have 2 carbon atoms that are attached to each other by a sigma bond. That is a single bond. And both of those carbons I've drawn as tetrahedron, or as tetrahedral centers. That is, there's 2 lines and a wedge and a dash for each of the tetrahedral carbon atoms. So what I want to do now is do an orbital depiction of the sigma bond. And I'm going to focus only on the C-C sigma bond. Okay, now what this looks like is we have a C with little lobe to big lobe. That's an sp3 hybridized orbital that's connecting that carbon on the left to the carbon on the right. And the carbon on the right has, again, a big lobe and a little lobe on its hybrid orbital. And the 2 lobes, the 2 big lobes, the 2 heads of those hybrid orbitals are overlapping. So if you look here, we've got head to head overlap, which recall is a sigma bond. Okay, if you notice, what we could do is we could kind of, I'm just going to redraw this down here, and I'm going to include the hydrogen atoms. Set a wedge. So now I've got the hydrogen atoms. What I want to make note of at this point is that if you take one of the carbon atoms and you rotate it, like let's rotate the left one relative to the right one. So if I take it and rotate it on my screen, hopefully this is fixed. In my hand, this is the left one. Maybe this is flipped. Anyway, so I'm flipping one of the sides relative to the other. I can do that, and I can spin that left atom and maintain head-to-head overlap. So even though the atom is rotating / spinning, so even though we're spinning now, and actually rotate is a better word. I don't know why I keep saying spinning. Anyway, so we're rotating and spinning. Even though that's the case, head-to-head overlap is maintained. If head-to-head overlap is maintained, then the sigma bond stays intact. So the sigma bond isn't going anywhere. It's not breaking or disrupting. So sigma bonds can rotate without disrupting head-to-head overlap and without breaking the sigma bond. Sorry to write this in sort of a negative tense. So these are things that sigma bonds can avoid having happened during the course of free rotation. That is, the sigma bond can freely rotate and maintain head-to-head overlap and keep the bond intact. Now I keep emphasizing this because the exact opposite is true for pi bonds. So if we look at pi bonds are, you know, if we had 2 carbons connected by 2 bonds instead of 1 bond. Okay, and then we have hydrogens out here. It turns out that now we're sp2 and we are trigonoplanar in geometry, which means we don't have to add wedges and dashes because there's no 3-dimensional component to the atoms that are bonded to each other now. Okay, so what does this look like from a molecular orbital depiction? So a molecular orbital depiction of this is very similar in one respect to the previous drawing. It's very similar in that the two carbon atoms are still connected by way of one sigma bond, but also one pi bond, and that pi bond just gets super awkward to draw. Recall that so these are p orbitals, and I'm going to do this little thing to indicate side-to-side overlap. Which is true of a pi bond. So we have side-to-side overlap, which is true of a pi bond. Now, side-to-side overlap is always awkward. You could see it was even really difficult for me to draw. I'm going to highlight the side-to-side so that you can see my side-to-side lines. It's hard to draw, especially in combination with the sigma bond, but both are present when we have a carbon-carbon double bond or any sort of atom-atom double bond. But here's the issue. For side-to-side overlap to exist, the non-hybridized p orbitals, which I'm showing connected by those yellow lines, those non-hybridized p orbitals must be parallel to each other. So during free rotation, I don't know what happened there. During free rotation, the pi bond would break as side-to-side overlap would or can't occur. So for our pi bond to exist, we need to have side-to-side overlap as shown by those yellow lines. And if that's the case, if we have side-to-side overlap, then we can't rotate because all of a sudden our p orbitals are no longer parallel to each other. And if they're not parallel, they cannot do side-to-side overlap, and we can't form a pi bond. So rotating, and so I don't know, I guess, the way to react to this is to just be sad. If we can't have a pi bond, if we can't have side-to-side overlap, we get no pi bond. Okay. What this means for us is that if we're going to have a pi bond, and pi bonds are awkward to draw, but if molecules can have pi bonds, they will have pi bonds, because pi bonds mean you can share electrons. And if you can share electrons, then you can get closer to your octet. So if we could have pi bonds, we will have pi bonds. And if we will have pi bonds, we won't have free rotation. As a result, pi bonds do not freely rotate. Pi bonds do not freely rotate. And that's an important kind of concept to grasp, is that for free rotation to occur, we must be able to rotate one atom with respect to the other one without breaking bonds and without disrupting orbital overlap. Okay, so that's a really good kind of segue into our next topic, which is conformational isomers. I guess I suggested we get there now, but just kind of going through this, it seems like let's just talk about free rotation before we move on to conformational isomers.